Right.
লেকচার 3 থেকে হচ্ছে গিয়ে এই যে এখান থেকে বেসিক্যালি। সো আমার প্রথম কোশ্চেনটা হচ্ছে কি স্যার, আমরা যে এখানে বেসিসটা নিয়েছি যে স্টেট, যে মানে স্টেটটা যেটা আছে এখানে আমরা সাইটা হচ্ছে কি অনলি ডিপেন্ডেন্ট মানে সাইটি দেখাচ্ছে। সো মানে আমার প্রশ্নটা হচ্ছে কি সাই কি শুধু এখানে, হ্যাঁ মানে কিভাবে হচ্ছে গিয়ে সে শুধু টাইমের উপর ডিপেন্ডেন্ট হচ্ছে মানে স্টেট?
Right. That's a very good question. Okay, let me address that. Right. So, psi is some abstract, vector in some vector space, right? Okay. So Ita's question is, why do I have only the time dependence, and where does the space dependence magically come from? Right?
Yes, sir.
Okay. So, this vector psi, this ket psi, lives in some abstract vector space. So I see Wajia has been able to join. That's good. So, let me represent this abstract vector space. It can be infinite dimensional, but we are bounded by our imagination, so we can only have something three-dimensional. So this is not a very good representation, but these are the axes, and we have some vector in this abstract space, and this vector, I'm representing it as a psi. Now it has a time dependence. What does this mean? What it means is that the time dependence is governed by Schrödinger's equation. So as time flows, this vector essentially rotates, because remember that the only thing that we care about is I have apparently turned on the auto okay, anyway. So what's happening is that the time dependence is governed by Schrödinger's equation, right? So we know that the way it changes with time is going to be governed by the Schrödinger equation, and if H is a time independent vector, then time independent operator, then the solution to this equation is that psi at some time t is given by the time evolution operator acting on psi at an earlier time. So what does this mean? It means that as time evolves, this vector it just rotates in some particular way in this Hilbert space. Okay, is that clear?
Sort of. I have to go through again.
Yeah. Well, it's just that the time evolution is essentially a rotation of your vector, of the state vector in a Hilbert space. That's all I'm saying, according to some differential equation. Okay, so the thing is that a vector is an object which is not dependent on its components. As you know from physics 1, a vector can have different representation depending on which axes you choose, right? So for example, I can say, I have a vector, say the velocity vector, which is this is something I talked about in a previous class, and depending on whether I choose, say Rahul's coordinate system, or say Ipshita's coordinate system, the components of the vector will be different. But the physical vector V is the same, The vector equation, so similarly, our physical state is represented by a vector, but we can choose to represent it in many different bases, okay? Now, what are the bases that are allowed to us? What are the bases that we are allowed to choose? According to quantum mechanics, if we have an observable, for example, the energy, the Hamiltonian operator, then we can choose its eigenbasis, which say, in the case of a discrete system, we can label it by a discrete index, corresponding to energy eigenvalues En. But we could have also chosen the position of the particle, which is the X operator. I'm talking about a one-dimensional particle for the time being. If it's three-dimensional, it's a vector operator with 3 components. And this operator will have eigenvalues, which are the position of the particle if you were to measure it, and that you could label the eigenvector by that eigenvalue. So what this is saying is that we can choose these eigenbases as our axes in our Hilbert space. So suppose that I choose this eigenbasis. Then now I have an infinite dimensional Hilbert space. So there'll be an infinite number of axes, and it could be, say, x1, and this is, say, x2, all the different points that the particle can be in, right? So now we want to, so now you see that we can want to now express this vector in this position basis. So we take components of this vector. How do we take components? We take the inner product. That is what we mean by taking the component of a vector. So we take x, which is a function of t because of the Schrodinger equation, and we take its inner product with the eigenbasis of the position operator, and voila, we have an object which has both a time dependence as well as space dependence. And this is what we call a wave function. So what is a wave function? A wave function is a position dependent function. By function, I mean it's a map from three-dimensional space as well as time, let's call it R, to the space of complex numbers. Wave function is a position-dependent function which are the components of the state vector psi of t in the eigenbasis, which I'm going to write as this, of the position operator. Okay? Isa, does that clarify how the space dependence comes out of something that apparently doesn't seem to have a spatial dependence?
Yes, sir.
Okay, good. All right, so as I was saying before some of you joined us, I am preparing a tutorial on the position representation for this coming Saturday. I'll get it to you as soon as possible, Ipshita, so that you can review the connection between the abstract notation that I'm using so far with the notation that you have seen in Quantum 1+. Okay?
Okay, sir.
Okay, so today I want to talk about angular momentum, but before that, I want to say a few words about stuff that we covered in the last few lectures. essentially, especially I want to talk about, the free particle. So what is the free particle? Oh, by the way, I also posted a note on the Slack channel about the problem 2 of the tutorial, which I think Nahi and other people were asking for, like, how can the inclusion of the potential in the Schrodinger equation pin down what the relative signs should be in the different terms of that equation. Okay, so do you want me to go over that here, or do you want to look at it and then maybe if you have questions, we can go over it in the next class?
So it would be good if we go over it.
Okay, sure. All right, quickly, let me just bring up my notes, which I also posted on Slack in the tutorial channel. So if you go back to the problem, you will see that you have 2 sign choices. One sign choice leads to a wave function psi1, and which in the notation of using the Euler formula is e to the power minus kx plus omega t. So here I'm assuming omega is positive, so that we are looking at, and if k is positive, we are looking at a left-moving wave, right? And this choice leads to a Schrodinger equation, which is I h bar del psi1 by del t equal to minus h squared by 2m del squared psi1 del x squared. Okay, but there was another solution possible where this, instead of minus I, we had plus I here. And that's it. But that led to a Schrodinger equation where we had I h bar del of psi1 del t equal to plus h squared by 2m del squared psi2 by del x squared. This should be psi2. Now, note that these 2 equations, let me call this, say, 1, and let me call this 2. Note that these 2 equations are related by complex conjugation and by identifying psi1, complex conjugation of psi1 with psi2, right? Which is exactly what we see here. Now, I'm not going to, I encourage you to go and work through it again in detail. If you want to derive from these equations, so these signs are determined by the fact that you want to have h bar omega equals to h bar squared k squared by 2m as your dispersion relationship. Now, if you were to want to add a potential to this, then a little thought will tell you, if you stare at it a little bit, that the equation that you have to satisfy is this, okay? So this is what would become equation 1 if you had a potential, and equation 2 then would become, again, it should be a 2. And now if you plug in psi1 and psi2 as before, but now the dispersion relationship is going to be different, what you will get is that from number 1, you will get h bar omega is equal to h bar squared k squared by 2m plus v, which can be interpreted as the energy is equal to the kinetic energy plus the potential energy. But from equation 2, you would get minus h bar omega is equal to minus h bar squared k squared by 2m plus v, which is going to give you E is equal to p squared by 2m minus v. Now, if there was no v, this minus sign didn't matter, right? Because they would cancel out from both sides, and these two would be the same. But because there's a v, these signs matter. And then you get an expression for energy which is wrong. And this pins down number 1 to be the right choice. Okay? So, in the light of these comments, I would encourage you to go back and look at your derivation and convince yourself this is the case. If you can't convince yourself, I will discuss with you more about this, okay? Nahi? Hello?
Okay, sir. Yeah, yes, sir. So basically, like for me, one of the things I came in, like I chose 2 type of waves, like kx plus omega t and kx minus omega t. So I don't know whether how my analysis would differ from the one you just showed.
So I'm only using one type of wave, but actually I'm using both type of wave if you think a bit carefully, because I am not telling you. I guess k cannot be negative, right? K is no, k can be negative. Yes.
Yes, sir.
Yeah, k can be negative because, and the whole thing only depends on k squared. So the sign of k is actually, but here I'm assuming omega to be positive so that I can identify h omega to the energy. So in that way, I'm actually considering both the left moving and the right moving waves.
Oh, yes, sir.
Okay.